Hello learners, welcome to the next session. Today we are going to discuss about the quantum Boltzmann mission. So here the first outline is quantum Boltzmann mission and key features of QBM, working principle of QBM and simple Boltzmann learning example with the help of RBM training. So Quantum Boltzmann mission is a generative machine learning model inspired by the classical Boltzmann machine, but it is based on quantum mechanics. It uses the quantum Boltzmann distribution derived from the quantum Hamiltonian to encode the probability distribution over the data. QBM aims to exploit quantum phenomena such as superposition and entanglement and to improve efficiency and performance in tasks like pattern recognition and data generation and optimization. The next key features of QBM is visible nodes represent the input data or observable variables. Next, hidden nodes capture complex correlation and patterns in the data. Next, quantum Hamiltonian governs the energy state of the system, incorporating quantum effects into the model. Energy function. The energy function is very important here. Hamiltonian means that the state of energy function and the state of the system can be inferred. Here we have the four steps are there. Initialization, introduce a group of random parameters as a rotating angle theta, state measurement, rotating angle into the quantum circuit and get the corresponding state, then operate measurement on the state. Then a sampling is there, repeat the step 2 and 3 and we can update the data and get the required output. So based on that we can go with that. So energy function here, energy function determines the probability of the state based on the energy, similar to the classical BM but extended to quantum state. Working principle of QBM, quantum state representation. A quantum state represents the complete information about quantum system. It can be expressed in two main forms, pure state and mixed state. In case of pure state, represented as vectors in complex Hilbert space, typically denoted as ket psi. For example, ket psi which is equal to alpha times of ket 0 plus beta ket times of 1, where alpha and beta are complex numbers satisfying determinant of alpha squared plus determinant of beta squared which is equal to 1 squared. Next is mixed state represented by density matrix rho, which generalizes the pure states to probabilistic mixture of quantum probability distribution. The QBM uses quantum Boltzmann distribution P of B comma H which is equal to e to the power minus E of B comma H divided by Z, where E of B comma H is the energy function of visible of V and hidden of H nodes and Z is the partition function ensuring normalization. The training process in the quantum Boltzmann machine involves optimizing the parameters, specifically the weights in the Hamiltonian, to minimize the divergence between the model predicted output distribution and the actual target data distribution. So simple Boltzmann learning example to be incorporated here. Here we are adapted the NumPy package and sigmoid activity function and initialize the RBM parameters. So the number of visible nodes and the number of hidden nodes and the learning rate and epochs. Randomly initialize the weights and bias values also. Based on that we can move the next sample dataset. And here we are adapted the training model with the help of contraceptive divergence. So what is the meaning of that is we are going to learn the pattern in the dataset by adjusting the parameters like weights, making its prediction match the actual layer distribution. So based on that we are going to compute the hidden activation. So the hidden value also to be computed and reconstruct the visible layer also. So the next is the recompute hidden activation for a reconstructed visible data and the weight updates also to be processed and print the epochs values. So this is about the execution. We are going with that Boltzmann process, and how it works is initialize the weights, positive phase, negative phase, update weights and training loop. So this is the basic Boltzmznn training model. For larger data sets and real-world data tasks, consider using the deep learning framework like TensorFlow and PyTorch for better efficiency. So different kind of applications are also possible: quantum modeling, generative modeling, quantum chemistry, optimization problem, feature extraction from data set in MNIST data set, dimensionality reduction, generative modeling for tasks like image construction or missing data prediction. Thank you learners, we will see in the next session.